Is this the pointer?
No, it's the left, right.
Okay, left, right, and the pointer here.
Yeah, oh yeah, sorry.
Thank you. So I am Seth Gossage. I'm a postdoc from Northwestern University. I'm going to be presenting some work I've done with collaborators from the CFA, Caltech, and Columbia University on convective turnover times in low mass stars. Maybe. Oh, there we go. So the first thing that I want to go over is how we can empirically determine convective turnover times. So we have this relation that Angstar went over, which we think is telling us something about the magnetic dynamo, where we have on the y-axis magnetic activity in the form of X-ray luminosity, and on the x-axis Rossby number again, which is this quantity, the rotation period of the star divided by the convective turnover time. And as Angstar mentioned, the convective turnover time is something that we don't really know what this is. We can measure rotation periods of stars, but we can't measure the convective turnover times of stars. But in order to get this relationship and calculate Rossby numbers, we need the convective turnover time. So how can we get it? One of the ways we can do this is by using the theory on which convective turnover times are based, and use this to calculate the convective turnover time via stellar evolution models. But another way that I'll go over briefly is that we can empirically determine the convective turnover time under certain assumptions. So one of the assumptions is that this saturated and unsaturated paradigm exists, where the X-ray luminosity is saturated at low numbers and it's unsaturated at higher Rossby numbers. And given this assumption, we can describe the X-ray luminosity as a function of the Rossby number in terms of this broken power law, where we have the sloped relation in the, or power law relation in the unsaturated regime, and this constant value that the X-ray luminosity takes on in the saturated regime. There are some free parameters here that we can then fit to this data using, for example, a Bayesian analysis, and then connect this the Rossby numbers back to our rotation period data that we measured for these stars and pull out empirical convective turnover times as a function of mass, or color in this case, as plotted for from Wright et al. 2018, the relation of empirical turnover time versus color. So you can see that the turnover time tends to increase with decreasing mass. We still don't exactly understand what these convective turnover times are. Right now, they're just a number that kind of gives us this nice tight relationship between the magnetic activity and the Rossby number. And you can see on the left, we have our magnetic activity versus rotation period data. When we divide this rotation period by the convective turnover time, we get this relationship, given all the assumptions that I mentioned. So I want to talk about our work in trying to answer this question of what these convective turnover times represent within the context of the theory that they're based on. And I'm going to first go over the new data that we're using in order to answer this question. So this is work that was carried out and led by Rocio Kimon of Caltech, and also with Christina Manch of the CFA, who are both here at the conference, where we compiled over 600 new stars and added this to the previous data set from Wright et al. 2018 from a variety of recent catalogs. We selected stars older than 500 million years old, so that they're all on the main sequence. And we can see our added stars in orange here compared to the previous data set in purple. We've added a lot of stars in the low mass end here, below about 0.6 to 0.1 solar masses. We've cross-matched with Gaia DR3 for accurate distance measurements, removed binaries and giants, and recalculated mass estimates consistently across all catalogs for these stars. This is what our full data set looks like, colors corresponding to the mass of the star, and our X-ray luminosity data versus rotation period, showing the magnetic activity rotation relation. This is what it looks like when we divide by the convective turnover times as determined by Wright et al. 2018, giving us the tight, nice relationship again. And we can go from this point in order to derive empirical convective turnover times according to this new data set that we have, using the same methods that I mentioned or outlined from Wright et al. 2018. So first, I'm showing you the empirical relationship again from Wright et al. 2018. Now the stellar mass is decreasing, going from right to left. And you can see the convective turnover time increase as the mass decreases. We have Gaia G band magnitudes corresponding to the lower masses here on the upper axis for comparison. And I'll show you what we derive with our new empirical turnover times using this new data set. So we have this conspicuous kind of bump here that is a new feature that's seen for the first time in this data that appears around the Zhao gap. So around the transition region where stars go from partially to fully convective. And we want to try to understand what's causing this bump in the context, again, of this theory that we're working with for the convective turnover times, to try and understand what's causing this. So we can go back to the convective turnover time, the theory that's it's based on. And the concept, as I mentioned, of the convective turnover time is theoretical, ultimately. It's not something we measure. It's based on this mixing length theory. And the picture is that we have, it's basically representing the characteristic timescale of convective motion. There we have these eddies here in the convective envelope. And this is describing essentially the timescale on which convective material rises and falls. It's in the context of mixing length theory, it's the basically pressure scale height divided by the convective velocity at position R within the star times this free parameter alpha MLT, which is a value that usually ranges between 1 and 2. So as you can see, this is a quantity in theory that can be calculated at any position in the star. Our empirical turnover times are essentially just one value. So it begs the question of where in the star do these empirical turnover times correspond to in the context of this theory? In dynamo theory and various studies, it's often thought that this convective turnover time should correspond to somewhere near the Tackle line for an alpha omega dynamo. So somewhere near the bottom of the convection zone, typically one pressure scale height above the bottom of the convection zone. And that's according to, for example, Gilman et al. 1980. So we've calculated models to calculate theoretical convective turnover times that we'll then compare to our empirical and try to learn a bit more about what's perhaps going on here. So we use MESA to model stars in the mass range of 0.1 to 1.3 solar masses at solar metallicity, using the same macro physics as MIST. And this is what our models look like here, using just those sort of classical calculations from theory, which match pretty well. And we were surprised to see that this matched so well just kind of out of the box with the empirical data that we saw. So if I plot the residuals here, you can see that for the partially convective stars, we do pretty well. The red shaded region here represents the error bars on our empirical data. And I'm showing here the residuals of the model convective turnover times minus the data. We run into trouble really around this fully convective limit. So I want to focus more now on this fully convective limit and what we think we can learn here and what's happening here and causing this, both this new feature, this spike, and also understanding a bit more what's happening in the stars, perhaps. So focusing on this fully convective limit and what we can learn about the dynamo from our results. So I'm showing you now a stellar profile of roughly one solar mass star at an age of 1 gigayear. We're looking at radial coordinate on the x-axis, and this is roughly the outer 30% of the star. And we have the radiator zone, you can see a little bit of that, and then the outer convective envelope here. We can calculate the convective turnover time according to theory, and see this is the run of it within the convective envelope here. It starts out small near the surface and rises as we go deeper in the star. And then we can ask where within the star do our empirical turnover times correspond according to these calculations. And in the partially convective stars, they correspond roughly near the Tackle line, near the bottom of the convection zone. And if we, as I mentioned, use the calculation, one pressure scale height above the bottom of the convection zone to calculate our theoretical convective turnover time, it matches pretty well as we saw for partially convective stars. I can show you the same thing as a function of mass, as a function of mass here. So on the y-axis now, I'm plotting the radial coordinate at 1 gigayear versus mass And we're showing the convection zone and the radiative zones as calculated according to our stellar evolution models. I'll show again the Zhao gap here. We have this transition from partially to fully convective stars. And this gray banded region here, which we're using as a proxy for the core boundary. It's just the where the energy nuclear generation rate, the nuclear energy generation rate drops from a value of 50 to 50% of its peak value down to 20% of its peak value. So we have, so as I applied in the previous figure, we have our empirical convective turnover times where those correspond to within these models, near the Tahoe line for partially convective stars, and then it looks like somewhere near the core boundary for fully convective stars. In our models, you can see they match, again, relatively well for partially convective stars, and we have this discrepancy around the fully convective limit. You can see we have this region here where the theoretical convective turnover times are existing at roughly this 20% of the stellar radius for fully convective stars. So this question about what's causing this peak, it's due to this rapid transition towards fully convective stars. It's in a relatively narrow mass range that the growing convective core comes to meet this deepening convective envelope that you see that all of a sudden our convective turnover times are being calculated closer to much deeper within the star, leading to a much larger value, giving us this peak that's reflected in both the stellar structure and in the convective turnover times correspondingly. And why it drops again, you can ask me about later. So that's this picture here. Almost done. Oops. As I mentioned, so asking about what happens with where you can think about the dynamo, it seems like this matches pretty well what we expected for a tachocline situated dynamo for fully convective stars. And our empirical data is suggesting that perhaps for fully convective stars, it's something like a dynamo situated deep within the star, perhaps at the core boundary. And the last thing I want to show you is this video just of the time evolution of the convective turnover time versus stellar mass. And you can see that this is the same figure I've shown you before, but it's going to evolve through time. And you can see how this morphology is dynamic, and that this is showing the convective turnover time versus age here with the 1 gigayear mark where I've shown you all the data before. This isn't to say that the theoretical values will ever exactly match to the empirical points here. There's a lot of confiscating factors that can go into this mismatch that I don't have time to discuss right now. But it's showing you that this morphology does change through time. And for more on this fully convective limit, I encourage you to go see Federica Chiti's talk at this splinter session later. And I'll leave you with my summary.
Introduce yourself for those people.
Hi, Zach with from Georgia State. You mentioned at the beginning that you remove binaries, and I was wondering what that process looked like.
Sure. Yeah, so I think it was just Gaia Rui. And then, so we probably have some sort of contamination from binaries still, we expect, but yeah.
That'll be word separation.
Yeah. So we have, okay, so the question was that what methods do we use to remove binaries? And I mentioned that it's the Gaia Rui that we use, and that there may be some contamination left. And it was said that that will mainly remove close separation binaries. And so that I think that's right. So we probably still have some contamination, but we're showing here that the binaries we have don't really mess with the morphology that we're fitting to too much. So we don't expect it will affect the results.
Unfortunately, we're out of time, so we're going to move on to the next speaker. That's thanks, Seth, again.
Very well.